Hello developers, let's start developing. So we're finally at the last task of this year's Advent of Code. It's task 25. And usually the 25th task only has a single part. So this is what you get. We are at the bottom of the trench. We have gotten to the seafloor, but there are a lot of sea cucumbers on it. There is a funny story that we're talking with somebody, and then we have a map of the sea cucumbers. There are actually two herds of sea cucumbers, and one of them are going east and the other ones are going south. So each location can contain at most one sea cucumber, the remaining locations are empty. The submarine generates a map of the situation, and that is our input. So each step they attempt to go one step to the east or the south respectively. But first they do an evaluation whether the field in front of them is or under them is available, and if it is, then they are moving simultaneously. So we have a two-step process: evaluate, move. And this is done in a strict way. East herd evaluates, east herd moves, south herd evaluates, south herd moves. So in this situation, the east herd will evaluate. This one cannot move since it has this guy in front of it. This guy can move and it moves. And after that, the south evaluates. So this guy moves and this guy moves as well because this one got out of the way. So one other thing is that this is some kind of a circular map. Yeah, so if you come to the end of the grid, you appear at the beginning. It goes same into both directions, both east, west, and south, north. So that means that first of all, these guys will evaluate, and this one can move, this one can move, this one can move, this one cannot. So after that, we will have these guys will evaluate, and this one guy can move, these two guys can move because this got out of the way. This guy cannot move because now there's a cucumber here, and this guy cannot move because now there's a cucumber here. And you can see that after one step. And if we continue so on and so forth, after a few steps we will get this. So a part of our task is that after a while the cucumbers will become locked, so to say. So if we have this initial step, after 58 steps we will have this situation where all of them are blocked and nothing moves. And that's all there is. If there was a second part, I would say that we would need to find the largest area that is available or something like that, because in order to look in they would need to be close to one another, I guess. Anyway, this is our input. Looks relatively straightforward, and to be honest, I have no idea how to solve this aside from a regular simulation. So let's start with that. This is our initial state. Let's call it. So first, of course, we're gonna solve the smallish thingy. So we just need to read all of it. Yeah. No, we're not parsing them. Line dot split on an empty string. So we're just getting the characters. And let's keep those characters. So this will be a string. There is no character in JavaScript, so we're gonna have to use a single length strings. And let's fix this thing up. we only have a single part, so that's all we need to do. And let's see if we are getting what we want to get. v dot v dot v dot vv arrow, and the last one is dot 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 v dot dot v dot arrow. Yeah, it seems that we are parsing the input correctly. So that means that we can have this move execute step, I will call it, and we will get a matrix as an input, which is an array of arrays of strings, and we will return a thing that has the matrix and the total number of moves. So basically yeah, let's have it like this. So we're gonna need to do something like this. Let matrix equals, still I'm gonna slice the input so that we don't actually break anything. We have the input untouched, and then we're gonna do while, yeah, and moves are 0. While moves are different than 0, and this is not gonna work, let's have this as -1. Yeah, that's clearly invalid. Let's have matrix and moves actually equal to execute step of matrix. Yeah. This doesn't work. Yeah, we're gonna need to do this thing that GitHub Copilot suggested, and it's smarter than what we wanted to do. Yeah. We're just moving them over and return the number of moves. No. Yeah, that's what we needed. How many steps? Which is the first steps on which node should secure compress move? So we might need to return step +1, I guess. But let's see. So this is our code. We are done, with the small difference that we need to do this. So what do we need to do? We need to evaluate east, move east, evaluate south, and move south. That's all we need to do. So we need to get all the east moving parts. Let's just map it. Or yeah, let's use a bit of typing here, because we're gonna have type cell. It will be either b dot or v or that. And so this is not gonna be a string array, this is gonna be a cell array. Cell array. Yep. What is the problem? Oh, this returns a string array. No, it returns a cell array. Cell array, cell array, cell array, and now we will have a problem here because it doesn't have an idea whether that's a cell array or not. Yeah, we're just gonna guarantee it. And this is one of the things that I like most about TypeScript, because it has a powerful type inference mechanism, but you can always take it into your hands and say, okay, you cannot know this, but I know this, and I will guarantee it for you. So these times I know. So basically, if we go in and put an X here, we will break that guarantee, but I'm not gonna do that. So how do we get all the east ones? And those are the brackets. So let's map this. Matrix dot reduce. Let's have it. Actually, let's write it in two stages. So if we have a row which is a cell array, what we want to have is to have row dot filter, no, row dot map everything to this kind of object. Yeah, I think I know what I want. Yeah, we're gonna reduce it, and we are having an accumulator and a line and yeah, and a Y. Is that a Y? Yeah, the rows are the, yeah, that's a Y. And then each row has an X. And we're gonna start with an empty array. And this doesn't do anything. And then we're gonna have line dot map everything to from a cell to an object, from a cell and an X, because this also takes two parameters, and we're just gonna map this to an object that's like this. So we will have X, it will have a Y, and it will have value which is C. And we're gonna push that to the accumulator. And then we don't need this because we're gonna return that. What is the problem? This thing that it returns a cell array. I'm doing something off here. What is the type of Y? It's a number. Account. Yes, it's that. And we are mapping this, and it returns an array of X, Y's and values. X, Y, value. Yep. I have no idea what I'm doing wrong, because from where I'm standing it seems to be okay. Let's extract this to an interface so it's easier to look at. Yeah, it's that. So this is a cell index. Okay, I didn't need to put the array type, I needed to put in the actual type. And now, no, this shouldn't return a cell index. It is correct, it should return a cell index array. So this is a valid, and as always seems that I am missing a parenthesis somewhere. So let's see, accumulator, which is a cell index array, we are pushing, and push exists, and then we have this. Let's extract this. Line is a cell array. Yeah, of course, y is not defined. This will return that one, and y is n. Let's have this as a one liner, maybe it will look better. And see why this doesn't say. Type number is not assignable to cell index. Oh, push as a method actually returns a number. So we don't need to return this, we need to return the accumulator, and to the accumulator add our line. So we need to have it like this, not this, this will be like that. And now let's see whether we have matched parentheses. So that parenthesis closes that, that closes that, and that means you just need this. Yeah, so I forgot what array.push does, returns. Yeah, that's the problem, and now it might even work without this. Well, it doesn't get that it's returning a cell index array. But on the other hand, why do we care? It thinks that it's returning an array of something that has x, which is a number, and y, which is a number, and value that is a cell, and that's what we have. So we actually transformed cell, or no. Why would it think that it returns a cell sometimes? Okay, we're gonna bring this back, and now it's a cell index array. So what we did was transform our matrix, and instead of using two for loops, which could have gone much easier, I wanted to use a fancy reduce, so this is it. So we're transforming our matrix into an array of cells. And yeah, let's log them out. And see what we're having. Yeah, we have this. So 0, 0 is V, that those are dots, those are everything. And now I can maybe even make this into a hash map. We're gonna have the cell and we're gonna generate a key which is x comma y. Yeah, let's have that as a method, so we can call it const to key, and that takes in a cell ci, which is a cell index, and returns ci.x dot ci.y. And now let's write out the cell map. So this is another structure which we don't need this if we have this. Do we? Yeah, let's keep it. It's not too much a hassle. We'll see if we don't need it, we can just take the value. So right now we have a way to do a quick lookup into this. So if we are at 1, 1 and we want to check what's at 0, 1, we can just ask that. So that will be a direct operation. It won't be a loop through all the cells. So we need to evaluate the east ones. So the east cucumbers moving east are just those. We can have all the cells and filter out ones that have a value that's going east. What kind of mapping? No, I don't want to do that. So these are the east cucumbers, and let's find which of them can move. So we got all the eastern cucumbers, and let's actually see them. Yep. And we're gonna need a result because I'm not gonna return the same matrix. I don't want to spoil the input. That's gonna be an array of matrix dot length, and we're gonna fill it with zeros and then map it to this that we're gonna fill with dots. And the result is a cell array. So we filled everything with dots. That's great. Okay, so for the east cucumbers, we filter out the ones that we want. We now just want to see which one of them will move. So we're gonna filter the ones that for each cell c dot x, the east ones are, so the way that we did it, this is the y and this is the x, so the east ones are increasing their x by 1. Okay, that's good. Let's increase the x by 1. Where the original matrix of cx plus 1, and now we're gonna do a trick in order to wrap it up. So if we have a matrix of 3 by 3, the indexes will be 1, 0 and 2, and if we ask for the index 1 we will get 0, we will get 0, for index 1 we will get 1, for index 2 we will get 2. So if we increase this by 1, it will become 1, index 2 and index 3, and there just isn't any index 3. But if we say something like give me 2 plus 1 modulo 3, we will get the 0. So it wraps up on the length. But let's write this out. That's c dot x plus 1 modulo, and let's have this as a constant. The width is that one, and the height is matrix dot length, and the width is matrix 0 of length. Yeah, I'm assuming that this is not a sparse matrix, but it's okay. So we're gonna have that modulo the width of the array, width of the matrix. So we need to return, and let's have the key. Yeah, let's have the key of that, and then we need to return whether cell map of key is equal to dot, whether that is available. If that is available, we are moving east. And let's actually do it this way. Map cell, we're not gonna do that. We're gonna do this. So we're not gonna filter, because now we will need to do the same exact thing, but the other way around. So we're gonna get the next index, we're gonna get that, and we're gonna return all the values with C, with the next one being the cell map of key. So we now have all these cucumbers and where they should be going. Yeah, so some of them will be going to an empty space, some of them are going to already occupied space. Let's see, 4 and 0. Yep, this one wants to go to another cucumber, this one wants to go to a dot, this one wants to go to a V on the other side of the screen, this one goes to cucumber, yeah. So it's easy to say now move east is actually the east cucumbers, which not next dot value, which have a next value of dot. And we're gonna have to, these are gonna stay, well, when the next is not a dot. So what we need to do, so for each of those that are moving east, we will need to set the result. Yep. No, y will be the same, but this will be next. This will be x plus 1 modulo of it. And for each cell of stay, of the eastern tribe? Well, we just do this. Those are moving and those are staying. And that is actually move east. So we evaluated them and we moved them. Okay, that's great. Now we need to evaluate the south ones, and it will be something like this once more. Only the south ones are facing a different field right now. All the south cucumber, because a south cucumber can have two issues with this. It can be blocked by another south cucumber, or it can be blocked by an east cucumber that already moved. Let's just first get the south cucumbers and map them. And this is the new index, and we need to get x is c dot x and y is the index, and the value doesn't matter. So we have the key. And we need to check this in two places. Or we need to modify the cell map. Yep. And we can modify the cells as well. Yeah, let's get the key. Well, we have a cell. Yeah, we need to write that a third time, but okay. So, cells of cell dot y, cell dot x is now empty, and cells of, okay, this is getting ridiculous, xx is actually this. I'm not gonna type it 20 times. So the cell of x is dot now, and the cell of xx is now an east moving cucumber, and cell maps map of key is equal to a, no, it's not a hash of unknown. T is the original array, and T is a cell index array, and U is a cell. Cell index. Yeah. Yeah, what do you know? Does it know? see the next is the cell index. Oh, the next is actually a whole thing with x and a y and a value. We actually need this, so we just dodge the bullet. And x is actually, yeah, we didn't need this. We needed cell.next.x. And that looks so much better and so much more logical. Yep. So the cell map of key should be basically, we're gonna recreate it. We're gonna say this is the original cell, only the value is now a dot, and cell map of next key is the original cell.next, and the value is now that. Yeah, this I can get behind. And if we're staying put, we're just staying put. So now the cell map and the cells array are updated. So we can just use the exact same code. South cucumbers, only we need the south ones. And then we're moving west, south. We're gonna have move west are the west cucumbers, south cucumbers, move south, stay south. When the next one is a dot, and we need to modulo the height, not the width. So this is move south, this is stay south. So if we are staying south, this one becomes a V, this one becomes a V, and this one becomes a V, and this one becomes a V. Oh, and we need to count the moves. Forgot about that totally. All moves is 0, and each time we move someone, we increase the number of moves. And return not matrix but result, and moves of 0. Oh, matrix is the actual result. So let's just do this once and print matrix, the matrix. No need for that. Let's just see what we have after a single move. This didn't find anything. Oh, did it? So after one step we should get dot 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 dot, something like that, and we definitely didn't get that. So this one didn't move, for example. which means that we might have a bug. Or quite a few of them. And this is the problem with this kind of things, that they are quite tricky to debug. So what we'll need to do is move over this to Excel. Let's have this. Let's separate it out. One more. And we have that. And let's see what happens here. Yeah. Huh? Come on. We just stepped over it like it was nobody's business. We have the height and the width, 9 and 10. Okay, the result is 9 by 10 matrix. Okay, the cell map is a cell map. So let's see the East cucumbers. We already said that this looks kinda okay. This one moves to that, this one moves to that. So move east, that's 10 that should move, and we have 13 that should stay. Okay, for which each one of those that is missing. So what is these values? It has 5 and 0, which means that the next one should have 6 and 0. Yup. And result of 6 and 0 is a moved thing. The key is 5 and 0, the next key is 6 and 0. Cells of 5 and 0 is a dot, becomes a dot. Actually it doesn't. Okay, this was a bit idiotic of me. Oh. Are we using the cells anywhere actually? No. So we're using just to get the V's, and those are okay. So, but if we're not using them, why is that a problem? Yeah, I think that we don't need these two, since they are quite incorrect anyway. And for anything else, we are using the cell maps as well. Terminate this run, let's start it again. So we're moving east. This key is 50, the next key is 60, cell map of 50. Did we mess up the X and the Y's? Not really. 50 is that, of 60 is dot. So the cell of 50 should become a dot. Okay, we should remove the next value, but for now it's kinda useful to find it in the list. We're not using that. So 60 becomes a V. That's a dot, that's a V. We're increasing the moves. Well, seems to be going okay. Let's see what the result has. The result has all these thingies. So this one won't move, this one will move, this one won't. This one won't, this one will. So in the second row we should have a one-off situation. Okay, in the third row this one won't, this one will, this one won't, this one will. So we should have a one gap and a two gap. Yeah, we have in the third row a one gap and a two gap. And now these two are adjacent, so this one won't, this one won't, this one won't, this one will, and this one will. That's all of that is okay. So seems that our result is quite okay, and on the last line we have this one that will move here, and it actually moved there. Cool. So let's see, we got all the south cucumbers. Let's see this one. At 0, 0, that's supposed to move at 0, 1 here. And we saw that didn't happen. So the ones that we need to move is 0, 0 here. Yep, it is. From move south. This is 0. And I'm an idiot. Let's just run this. And now let's see if we find this in the description. Yep, got it. So let's see the situation after 57 steps. Doesn't is different from 57. Let's just run this. Am I printing the matrix each and every time? Yep. I just need it once. Last time. This looks like something in. Let's see what it is after 56 steps. Yep, we have the correct count. So after 56 steps, when our steps are 56, we have 56. So we stop moving after 58 steps. So we can return moves doesn't equal 0 and return the steps. Let's see if this thing runs. And whether we're getting 58 or 1. 1. That's weird. So this thing says that we made 0 moves. That's on the weird side. So it seems we're doing everything correctly except counting of the moves. New moves is 0. Why? Let's look at that. Do we do that? Do we do that? We do everything that we want to do, we're just not returning it. We hard-coded this part. Yeah, so those are plenty of smallish errors that need to be rooted out, otherwise we won't get the correct answer, and we got it. So let's now see what will happen for the huge input. This is a bit bigger than our original, and let's just run it and see when we get to a solution. Since we're doing a straight up simulation, there's just no way to speed this up. I mean, we can do a better management in the step-to-step processing. So let's kill this here, and let's start it here on the waiting place where we can wait. Once again, I'm gonna off to walk the dog, and hopefully by the time I return we will have a result. So we're back, and this thing didn't produce any results, it just stood there. So most likely we have an issue in our code. Let's take the small input again and let's take a look at what happens. It's 115 milliseconds, so this should be about 100 times bigger, so I would expect something like 11 seconds. And we didn't get that. Even after half an hour of running, it didn't give us anything. So what we can do? One of the things is that we're executing steps, so let's just log the step. Let's see how long it takes for a single step. And I don't know about you, but it seems that we have a problem in the step itself. It's not that this is running for thousands and thousands of steps, because that's one possibility. One possibility is that we have a situation somewhere around here where we will run for millions of steps and never finish. But it seems that we're not processing even a single step. Okay, so back to the debug. Let's see what happens here. Yes, we're getting the height and the length, that is instantaneous, and it's 137 times 139, so it's about 200s, and we're getting the result, which is a full-on matrix which has only a lot of dots, and that is quite fast. We're getting the cells, and the cells is a length of 19,000 items. Okay, and that was fast, and this is the problem. Yeah, I didn't expect this to be the problem, but apparently this is the problem. This went away and died on us. So what's inside the toHash method? Yeah, you can see that it is extremely small. We're getting a selector, a processor, and processor basically in our case is items arrow item. So this is the code of the default processor. Just take the item. And we're taking the accumulator and the item, and we're returning a new object which has all the properties of the accumulator, plus uses the selector to generate the key and uses the processor to generate the value, and we're starting with an empty object. So yes, this is the problem. The issue is that JavaScript object creation is basically C++ object creation, and C++ object creation uses some memory. So in this case, from 19,000 items, for 90,000 items, we are generating basically 18,999 objects that are immediate garbage. So on each run of the reduce, because reduce is just a fancy for, on each run of the reduce, we are generating a new object, and in the next run, that object is already garbage. And that uses up a lot of memory. And usually it's not a problem, because as long as we have enough memory, everything runs smoothly. So I'm not gonna change this method. I'm not gonna fix the method itself. And but the issue is that once we use up the available memory, we know that we have a lot of garbage, but we need to collect that garbage then, and then we have a lot of memory that is scattered throughout the memory mapping. So usually these kind of methods that use an inordinate amount of memory, so in 99% of the case they are totally fine, but there is 1% where we are experiencing what's usually called a performance cliff. So, for example, this might work great for 10,000 items, but it will last a second for 10,000 items, but for 10,020 items, it will be an hour, because we run into the garbage collector. So I do need to add a comment here. This is not okay for large arrays. Yeah, so we're gonna need to do something like that. Reduce is great because it gives us, so to say, immutability. We give us constancy. We have a single line and we just get everything that we need. So this is a good method, but we're gonna need to redo it. So let's see if this makes sense. So we're gonna start with an empty object, and now we're not gonna create a new object on each run, but we will just loop through all the cells and then cell map of, yeah, just use this. Let's see if this works better. It should work much better. That's one way to find out. I will just let it run. Yeah, and we got the cell map, which as you can see, is a huge object with a lot of data inside of it. So let's run this once. Yeah, so now we're moving steps. Step 7, step 8, step 9. It's not the fastest, but I can live with this. Let's just say if step mod, and I'm going to use 10, is equals 0, then print out the steps. Yeah, let's see if this thing, oh, we need to kill this and let's restart it. Yeah, so we're getting about 10 steps per second, which is not great, but not terrible as well. And let it run. And it finished in 20.5 seconds, and it told us that our result for part 1 is 380. Let's check if that is actually correct. The 58 was correct, and that's the right answer. We are one gold star closer to finding it. Suddenly the experimental antenna control console lights up. Slide keys detected. Yeah, we detected the slide keys. The keys are directly under the submarine. You landed right on them. Using a robotic arm on the submarine, you move the sleigh cars into the airlock. You just need to get them in Santa to save Christmas. You check your clock. It is Christmas. Yay! By the way, Merry Christmas to everybody who celebrates Christmas on this day. There's no way you can get them in surface to task. Button on the slate keys. Remote start. You can start the sleigh from the bottom of the ocean. You just need some way to boost the signal from the keys so it actually reaches the sleigh. The submarine has the experimental antenna. You'll definitely need 50 stars to boost it that far. Energies. We are starting the antenna and says slate key is done, installing device drivers done, recalibrating antenna done, boosting the... Yeah, so we have 1 star. As I said, we are given 1 star if we reach this far. So we have only 49 stars to go, and we actually have 47 stars. You don't have enough stars to boost the signal, though you need 2 more. Yep, that's the case. So for Advent of Code, we're gonna need to solve 22 second part and 23 second part. But those will be in their own videos, and at the end we can watch the grand finale where I guess we will get some animation of the sleigh running or something like that. So we had another solution. Let's check if this is the slowest one yet. We don't need this. We can run start, and it will just sit there for a couple of seconds, and then it will tell us the result. Yep, it's correct. Let's run all the tasks except task 19, which will need to have also a separate video because it takes around 20 minutes to run it. So this is it, and yeah, this is way too slow, as we cannot have one thing have 60% of all the runtime. We might need to optimize this as well, but we'll get to that when we get to that. So far we have a lot of tasks solved. Total runtime is 23 seconds plus 20 minutes for 19. So looks okay for now, and see you when we are doing the second parts for the 23rd and the 24th tasks. 22nd and the 23rd task. Goodbye for now, and keep developing.